Alright, hello YouTube. Today we're looking at another LeetCode problem. This one is 3-sum. So 3-sum is one of the first LeetCode problems. If you've already seen 2-sum, then this is kind of built on top of that. If you haven't done 2-sum already, as well as 2-sum's variants, do a couple of those. Do 2-sum and do a couple of 2-sum's variants, or at least solve 2-sum in different ways. I won't say the ways to solve it, so you can go to that, but you want to pause this video, go solve it, come back, and I'm going to talk about the different ways that that was solved and how we're going to solve 3-sum. Okay, so before we get into all of that, let's just talk about this problem. So this is a medium, and let's read the description here. So given an integer array nums, return all the triplets nums I, nums j, nums k, such that I is not equal to j, I is not equal to k, and j is not equal to k. And nums I, j, and k is equal to 0. Notice that the solution set must not contain duplicate triplets. Okay, so that's another thing. Okay, so it seemed like from the description we kind of have 3 rules here. And the first one is none of the indices can be the same. So we can't all take the first index repeatedly, like 0, 0, 0. If the first index is equal to 0, we can't do that. Second rule is that the 3 indices that we choose must equal 0, and we must not have duplicate triplets. Okay, so let's look at the example input here. -1, 0, 1, 2, -1, 4, or -4, and okay, we're looking, given this input, what 3 values, 3 indices, or indexes end up adding up to 0. Okay, so we could just do 0, 0, 0. However, remember our indices can't be equal. Okay, so we can't do that. So let's look at 3 unique index that equal to 0. So -1, let's say we have -1, okay? All right, -1, 0, and 1. Okay, that does equal to 0. So we'll add that. We see that's one of our outputs. Now, what we mean by cannot contain duplicate triplets is, okay, we just added -1, 0, 1 on there. Okay, 1, 0, -1 is the same thing, but it's just in a different order, right? So that would be a duplicate. Just because it's in a different order, it's still the same values from the same indexes. So we can't do that. It's got to be unique. Okay, so now we know which values add up. We've pretty much explained all 3 rules here. And for -1, -1, 2, let's look at that. So -1, -1, and 2. Okay, so how did they get to that? Well, -1 plus -1 is -2, plus 2 is equal to 0, so that's another value. And then I don't really see any other occurrences on here that would happen. And then there's an explanation here. These are distinct. Notice that the order of the output and the order of the triplets does not matter, right? Okay, and then example 2. Here's some edge cases. So this one is where there is no solution. So 0, 1, and 1, there's no solution there because we're adding them. And the only thing we can do is add 1 and 1. So our output's going to be null. Okay, let's look at the constraints. So if nums.length is less than 3, then we'd have to, but it looks like that it's going to be at least 3. Okay, so we don't have to worry about it being less than 3. And then the values are going to be held within an integer, so we don't need to use long or anything like that as well. Okay, so let's talk about the approaches. So with 3-sum, there's probably a few different ways to solve this, but I'm going to talk about one way. And when you solve 2-sum, if you solve 2-sum, it'll make this problem a lot easier. And the way that I recommend solving 2-sum, and you can also, so I recommend solving 2-sum with a 2-pointers approach. And if you don't know 2-pointers approach, go look that up on Geeks for Geeks, figure out how to do that. and apply that to your two-sum problem before you come here. And we also keep a hash map. Now, with two-sum, for the very easy way to do it to start out with, before you know all these different things, you could do a brute force approach with a nested for loop that goes through I and then j for each one. And for threesome, theoretically, you could also do that to generate every single triplet order that's possible. But then we're looking at what, like, into the third time complexity at least. So that's just extremely inefficient. So how can we cut down on that? Okay, so we're going to use the two pointers approach. So let's dive in with the two pointers approach, or at least explain how we're actually going to utilize that. So let me think. We have these three indices, and we want to use a two pointers approach. The first thing I want to do is sort the array. So I'll do an arrays.sort nums. All right, and then we also need our return value. Result. New array list. Okay, so, and then we'll just return result list at the bottom for right now, so it quits barking at me. But, okay, so we have kind of a really basic setup here. So we're going to solve this with a two pointers approach. My intuition here, and we'll write out the intuition before we go into coding. That's usually a good idea. And if you're with an interviewer, it's a good time when you write out your intuition of how you're going to solve the problem, that they'll be like, hey, or they might drop hints for you at this time, be like, hey, maybe we could do this instead, or did you think about this approach? So let's talk about our intuition here. I'm thinking that we do a single for loop. Okay, so first thing I'll say, we need to look at three values at once because we have triplets. How? I'm going to say that we do that by, we do a for loop. So that's one value. Then from that value, say it's at the start of our array, we have a left and a right pointer, where left is I plus 1 and right is nums length. Anyways, okay. Okay, so that makes sense, right? So we're going to say for this one, and we're going to start off at this input. Here's I, and then left and right. Okay, so we're looking at three values. Now, we see if those three values equal to 0, which they don't. Okay, so -1, 0, and -4 is equal to -5. Well, actually, okay, for the two pointers approach that we're using to work, for this two pointers approach, you have to have the array sorted. That way we can calculate the values and move the pointers correctly. So we need to actually sort this. So let's look at this approach. Example sorted, and we'll say this is what? -4, -1, -1, 0, 1, 2, right? 6 values, okay, yeah. So, all right, now we have -4, 2, and -1, which is -5 plus 2, -3. First run is equal to -3. And then we're going to continue. So what do we do when our value is -3? We want it to be closer to 0. And since we have a sorted array, we can get closer to 0 by getting rid of or moving forward with our left pointer. That way it's approaching a higher value. Now, I'm not going to go through this entire example because we know that if we have this -4, there's going to be no values that are going to equal up to 0 unless we could use 2 twice, which we can't. So that example is bad. If we move on to our next iteration where it's -1, okay, we can do this maybe, right? So now it's -1, left is -1, and right is 2. So -1 plus -1 is -2 plus 2. Now that equals 0. So that's an answer here. -1, -1, 2. And do we see that? We do see that in the output. So there is, bam, an example of this. So we have that. That's great. Now we could end up with one other issue, and that other issue is going to be duplicates. Now we don't want to have any duplicates. So how can we not have duplicates? I think that if, like, so say that we have I already equal to its value before it. So -1, -1, 2. Okay. And then we move this up, and then we have -1, 0, 2. So I think we're actually going to encounter a duplicate. So we'll go through this example just to figure out how we're going to handle that. Okay, so let's go through a run here. I is equal to 0, 1, 2, so 2. So we're going to start at -1, the second -1. Okay, so now left is equal to 0, right is equal to 2. So now we have -1, 0, and 2. That's going to equal out to 1. So we need to move our right pointer left 1. Okay, I is equal to 2. The second -1. Left is equal to 0. And right is equal to 1. -1, 0, 1. Perfect. Okay. Now we have -1, 0, 1. And that is a value. So now that we have done this has occurred. Then we're good. So we have this example here of -1. So here's another. Okay, so I think that what we're kind of getting confused here, this is actually, this run that we just did is going to be our duplicate run. We get to the first -1, and we do left and right here, -1, 2, and that's not going to work. And we do -1, sorry, -1, -1, and 2, that does work. So that's great. But then when we have that working, and we find a correct one, as long as left is not greater than right, or whatever our condition is that we stop the loop, we're going to increment left and decrement right. That way we're continuing to look through all values for I. Because if we just grab the first one and we quit, then we may not grab all values. Which is actually what happened there. What kind of tripped me up. So say we grab -1, -1 and 2. That's great. And then we move forward left. So instead of it being -1, now it's 0. Remember, we're keeping I because we're formulating every value possible with this value of I. So now left is 0 and right has moved down, which is 1. So now we have -1, 0, 1. Okay, well, when we just did this earlier, for the second I, we had -1, 0, 1. Okay, so that's a duplicate. How can we avoid the duplicate? Well, if we did this with all of these values, -1. Say when we move up to this one, and I is going to be equal to the second one, the only value that we ended up getting out of there, we had already calculated because these values are the same. So if we ever occur on an I, say we get to this I, and it is the same as the previous one, we've already calculated all possibilities with this one. So we can move forward until we're to a unique value. And I think the same can be said for left and right as well as we're recursively going. So we already had like one and we had another one here like that. Then we could move right over until we're at a unique value, and the same with left. If we had a -1 here, then we would move the same. Okay. Okay, so we've done the example. I think we've kind of built out our intuition well enough. I think we can kind of go through this problem now. So let's do an int left equals 0, right, and I think we can do that. Go ahead and declare the value for that. And we also have I think it's just left and right. Do we need a sum? I don't think we need to declare the total sum outside of the for loop, because we're not like tracking a persistent value. Okay, so here's our I loop that we were talking about. Now, okay, so actually we don't need to declare left out here because left is going to be I plus 1. Right. Okay, so if I is not equal to 0 and num sub I equal to num sub I minus 1, continue. So we'll go to our next iteration because we've already calculated all values with that possible one. All right, now we have our big boy logic. While left is less than right, and total sum is equal to num sub I plus num sub left plus num sub right, and right is actually going to be length minus 1 because it would be an out of bounds index error. Okay, so now we're going to do if total sum equal to 0, that means that we have a value that matches these indices that match, and we're going to want to add it onto our result list integer addition new array list. Can we do it in here? Arrays as list. I'm not sure if that's possible. I think so. Maybe it was, and I just should have. Geez. Okay. I think it was just mad about the We'll just do it this way since we already got it out. But I think the other way was possible. Can I convert from list integer to integer? I think, okay, let me actually do this. So do we even need to do that? What about result list? Okay, yeah. I think I was just thinking way too deep into that. So we can add that arrays not as list. We're generating a list there. Okay. Now we have found our value for a total sum. Now we need to also, while we're here, we need to do a left plus plus and a right minus minus. Remember, because we're calculating every single value. But on top of that, while left is okay, so this is while nums. This was our while nums left is equal to nums left plus 1. Now, we don't want to go out of bounds for this left plus 1 while we're calculating. So we could do like left is less than right for this for sure, because right is going to be within bounds for our case here. And left is equal to left plus 1, left plus plus. Okay, so we need to also do right. So while right is greater than left, because we don't want to overlap right, I think that should work. And num sub right, do num sub right minus 1, right minus minus. Else if total sum is less than 0, we will do while the value of total sum is less than 0, then we need to increment left. So we'll do left plus plus. Else right plus plus. Okay, so I like this solution. I think that this may be all we need. Let's go ahead and submit and see what we think here. Okay, so we end up getting an index out of bounds error. Why is that? Left is initially and this is for 0, 1, 1. Okay, so this has got to be something simple. So I initially is at 0. And then left is at I plus 1. And then right is at nums.length minus 1. Nothing occurs. So we're actually going to increment right plus, yeah, not right plus plus, right minus minus. Okay. Okay, so we're not passing all of our test cases here. So something with our logic is wrong. So -70, -60, 130. Why aren't we picking up on this? 70, -50, 130, and Well, that's sorted. We're not going to pick up due to. And we're only passing 74 test cases, so there's something truly wrong here. I think that the right needs to be inside of here as well. This is one thing, because as we do right and we're moving it around like we do left, we need to, on the outside, reset it for each eye. So that's one problem. So I think that might be it, because we're only going to get the first output correct every time. Okay, that was it. Yeah, okay. Sometimes it's the small things, but just remember that's something definitely that makes sense. So sometimes it's the small stuff. But yeah, left, right, that is three-sum. The sorted approach with the two pointers approach is used for two-sum too. This is just a bit more convoluted because we have to worry about the duplicates, which is solved through, these occurrences with the while loops here. Yeah, for this one, so I think the space complexity is going to end up being O of k, where k is the number of triplets that we're inserting into this result list. And for our time complexity, we have a single for loop, so that's O of n off the bat. Then we're using a two-pointers approach. So worst case scenario, for every I, we're visiting every other index within once. So that's doubling up on that. So worst case, I think that we're looking at quadratic time complexity, or n squared. So, all right, well, that's two-sum. Thanks, guys, for watching. Take care.